Hello and welcome to our first lesson of Chapter 1. In Chapter 1, we are going to talk about transforming functions. So this is going to include moving functions left, right, up, down, which we are going to do today. This is going to include flipping functions over an axis. So like flipping an entire function over, say, the x-axis, like it's a mirror. And this is going to include expanding and compressing functions. So if I take a graph and I stretch it up so that it's taller than it was before, or stretch it out wider, or squeeze it in narrower, or squeeze it down shorter. So today we are going to start with just moving graphs left, right, up, down, and looking at how can we tell if that's going to happen, how do we tell that from an equation, and how do we figure out an equation from a graph. So our first graph that we have shown here is the graph of y equals 1 over x. So we know from grade 11 that this is a rational function. That's what this is called. Okay. And this rational function has two asymptotes. It has an asymptote along the x-axis and an asymptote along the y-axis. The asymptote along the x-axis is our horizontal asymptote. And we write that as y cannot equal 0 because y is 0 everywhere along the x-axis. We also have a vertical asymptote along the y-axis. And that would be x cannot equal 0. Okay. So our job here is going to be to try and graph these two functions that you see on the left, y equals 1 over x minus 2, and y equals 1 over x all plus 4. These are both rational functions as well. So our first thing is we're going to try and figure out where our asymptotes are to help us graph these. Our first graph, y equals 1 over x minus 2, in order to find our horizontal asymptote, we know that for our rational functions that look like this from grade 11, our horizontal asymptote will be y cannot equal 0. This will be true for any any rational function that looks like this, okay? So this has a horizontal asymptote, y cannot equal 0, which is true for any rational of the form y equals 1 over x plus or minus some number. We can just call this some number b. Okay. You might also have a coefficient in front of your x, so I'm going to put an a here because if you have something like 1 over 2x minus 5, that will also have a horizontal asymptote, y cannot equal 0. Now our vertical asymptotes, if we remember from Math 11, are wherever our non-permissible values are. So we need to look at the bottom of this function and say, what can x not equal? So we're looking for what x value would make the denominator 0. And here, if x was 2, our denominator would be 0. We're not allowed to have a denominator of 0, so that means x cannot be 2. Vertical asymptote would be x cannot equal 2. Okay. We're going to now plot these on our graph. So y cannot equal 0. That's along our x-axis. X cannot equal 2 would be a vertical asymptote over where x is 2 there. And then we need to pick some values that we can plug into our equation so that we can find some points. So if you want to make yourself a little table of values, you can. You might find that helpful. You don't need to. You can do it in your head if you'd prefer. And I usually start by picking one value on either side of my vertical asymptote and go from there. So for here, my vertical asymptote is 2. So I'm going to at least want to pick 1 and 3 to plug in. If I plug 1 in, I get 1 over 1 minus 2, or 1 over negative 1, which is negative 1. My point's going to go here at 1, negative 1. If I plug 3 in, I get 1 over 3 minus 2, or 1 over 1, which is just positive 1. So I'm going to have a point over at 3, positive 1 here. This tells us that we know that our L-shaped portions of this graph, those curved bits, are going to be up in the top right corner and the bottom left corner where these blue dots are. I do need a couple more nice points to be able to graph this nicely. They don't need to be perfect because your points are not going to be perfect. So for example, I might want to pick now a value of maybe 4. So if I plug 4 in, I get 1 over 4 minus 2, or 1/2. So if I put that point on my graph, it's not going to be on a nice grid line. Okay. If I plug in 0, 0 might also be a good one. I get negative 1 over 2. So that's going to go here. Now if I keep going to the right of my rightmost blue dots, like if I keep going over here in this direction, what's going to happen is I'm going to just keep getting smaller and smaller values that are harder and harder to graph. Instead, I might want to try and pick something to the left of this point here, but I can't go very far because the asymptote is in the way. So I might want to choose maybe 2.5 and plug that in just so that I can get another nice point. So if I pick 2.5, let's fix my graph up a bit so I have spots to do that. So I had 3 and 4 here. I'm going to add 2.5 in. Okay. At 3 we were at 1, at 4 we were at 1/2. If I plug 2.5 in, I get 1 over 0.5, which gives me 2. So my next point to the left of my blue dot here, but still to the right of my asymptote, is going to be at 2.5 and 2. Okay, so again, once you've plotted that first point on either side of the asymptote, it gets a little bit icky with the points. They are not nice, but having another 1 or 2 or 3 points to be able to plot this curve is helpful. And when you put this curve in, because you are not a computer, your curve is not going to be perfect. We know that we could also try 1.5 to the left of the asymptote, but to the right of this point here, somewhere in here. And if I plug that in, I'm going to get negative 2. So you can add that to your table if you want, or we can just plot it. And it's going to look like this. So now the question is, if I compare this to the original graph I had, what happened? Okay, what moved? Well, my horizontal asymptote did not move. My graph did not move up or down. If I look at the nice point from my original graph, those are here. So what has happened to those points is they have moved to the right by 2 here. Right? That point has moved there. That point has moved there. The asymptote moved. My asymptote was originally on the axis. Now it's at 2. Everything has shifted to the right by 2. I'm going to erase my arrows just because I am going to be graphing another thing here soon in a minute. So this is 1 over x moved right 2 units. Okay. So if I changed this and I wanted you to graph, you don't need to write this down, but y over x minus 5, that would move to the right by 5 units. Or y equals 1 over x minus 10, that would move to the right by 10 units. Okay. If I changed it to x plus 5, that's actually going to move to the left in the opposite direction. Or x plus 10 would move to the left by 10. We're going to try this next one that looks a little bit different. Okay. We can see that we have 1 over x all plus 4. So the problem here is that our horizontal asymptote, we don't look like our case above, right? The 4 is not in the fraction with the x. Okay. So this here has a horizontal asymptote of 0, right? So if I take that and I add 4, what do I get? I would get a horizontal asymptote of 4. Now, what about my non-permissible values? What can x not equal? If I take a look here, x cannot equal 0 because we cannot have 0 on the bottom of our fraction. So if we draw these in, we have x cannot equal 0, which is along our y-axis. And we have y cannot equal 4, which would be our horizontal asymptote. Okay. Now again, if you want to make a table of values for yourself so that you can actually plot the curved bits, you may, or you might do that in your head. So we know we can't have an x value of 0, but I could have -1, -2, I could have 1, I could have 2, those are all okay. So if I plug 1 in, I get 1 over 1 plus 4, which is 1 plus 4, which would give me 5. So I'm going to have a point over at 1, 5, which would go up here. If I plug 2 in, I get 1 over 2 plus 4, which would be 4.5. So I'm going to have a point over at 2, 4.5. So we can see this is starting to look like the blue curve we drew. It's just up a little higher. Okay. If I try -1, I get 1 over -1 plus 4. That would give me -1 plus 4, which gives me 3. So I'm going to have a point at -1, 3. If I plug in -2, I get -1/2 plus 4, which would give me 3.5, which would go here. Now again, if you want to pick some points that are closer to your asymptote than those, we could pick, say, 0.5 or -0.5. If I plug 0.5 in, I'm going to get 1 over 0.5 plus 4, which would give me 2 plus 4, or 6. And I get a point here. I can connect my curve. Remember, you cannot cross that my green dotted line, my asymptote. And I can do the same thing on the other side. I could plug in -0.5 if I want, and I would get -2. So then the question is, what has happened here compared to our very original graph, not the blue one that I drew earlier? Compared to my original graph, what happened? Well, again, if I compare these nice points that we started with, what happened to those? Those moved up by 1, 2, 3, 4 units there. What else moved was our horizontal asymptote. Our horizontal asymptote also moved up by 4 units. Okay, so this one is 1 over x moved up 4 units. Okay. Now, you might not be given a function of something that you know. You might be given some random graph. You might not even be told an equation for that. You might just be told this is some function f of x. So for this next one, this is the graph of some function f of x. We don't actually have an equation for this. We just know this is a function and this is what it looks like. So we are asked to figure out what sort of translation is happening. So if we think about what we just did, we saw that if we subtracted 2 inside the function with the x, we moved to the right by 2. So for this one, which of these has something inside the function with the x? This one has something inside the function with the x. That means that's going to be moving left or right. Now earlier we moved right when we subtracted 2. So this one, we are not subtracting 3, so we would not be moving right. We would actually be moving left. So what that means is when I'm looking at this graph, all I'm going to do is take all my nice points and move them left by 3. So I like to start with the leftmost point, move it first, and then connect the dots as I go. So this point is going to move to the left by 3, which is going to be slightly off my grid. My next nice point is this one here that's on my y-axis. If I move that to the left by 3, I end up here. And I would suggest you connect those points now. When we start getting into flipping the graphs using reflections or expanding them or compressing them, many people who do not have great visual skills will find it very difficult to connect the points if you don't do it as you go. So I would very much suggest you connect the points as you go. The next point here, move to the left by 3, connect the points. And the last point, move to the left by 3, connect the points. So you can see that the graph has not been stretched or squished, it's not been flipped, it has simply been picked up and moved to the left by 3. The next one we see, the -2 is not inside the function with the x, but rather being subtracted on the outside of the entire function, which is similar to the second graph that we saw above. The second graph we saw had a +4 being just sort of tacked on to the end of the entire function, and that moved our graph up by 4. This one, we see the -2 tacked on to the end of the function. This means we are going to move down 2. Right? So if I take these same nice points I had before, I take the leftmost one and I move it down 2. The next point, down 2, and connect the points. Okay. The third point, down 2, connect the points. Last point, down 2, connect the points, and we are done. So we can see here that we have the purple graph has simply been moved down by 2 units. If you're feeling like I'm going too fast because this is a video, a reminder that you can pause at any time. You can also play the video back at something like 2/3 of the speed or 75% of the speed. If you're finding I'm going too slow, a reminder that you can skip forward in the video if necessary, or you can even speed it up and watch it at 1.5 times the speed if you're finding that I'm going too slow. I do like to go a little bit slower on the videos because I tend to start talking a little bit too fast, and I'm hoping that everybody can follow along. So if I am going too slow for you, feel free to skip forward, watch it at a faster speed, and if I'm going too slow, remember you can always skip back or pause. So our general statements for any sort of moving left, right, up, down. If we replace x with an x minus k in our function, it's going to look like f of x minus k, meaning it's inside the function with the x. This is a horizontal translation. Okay, meaning left or right. Often you will see this written as HT for horizontal translation by K units. Okay, so this means left or right. Okay, so an example, if you see your function as f of x minus 3, this is going to be moving right by 3. If you saw f of x plus 3, this would be moving left 3. It's a little bit counterintuitive. We usually think of plus as the positive side of the x-axis, but here, if you see a plus inside x plus 3, that's actually moving left 3. So it's a little bit counterintuitive with the x's here. Most of you will need some practice to make sure that you know which direction you're going. If we have a y replaced with a y minus k in our function, just a reminder that f of x can also be written as y. Okay. This is going to be a vertical translation by k units. So what this will often look like is y minus k equals f of x. I personally don't like to have the k on the same side as the y. I like to have it always written as y equals. So I would choose to rewrite this as y equals f of x plus k. And that's why you can just look at this and say, okay, this is going to be plus 4, up 4 if there's a 4 added at the end. Okay. If it's written as the first version, it's going to say y minus 4. Okay. So this is a vertical translation by k units. Vt, you might see that written as. And so this is up down. So an example, you might have this written as y minus 4 equals f of x. I would rewrite this as y equals f of x plus 4, and this would be up 4. If you had something like y plus 5 equals f of x, I would rewrite this as y equals f of x minus 5, and this would be down 5. Okay, so please note, if you do see this written as y minus k equals f of x, you are allowed to rewrite this as y equals f of x plus k. So that would be my preference. I would rewrite this. So we're going to try one where we have to do both types of transformations. So the first thing is always try and figure out what is the base function. It's usually much easier to graph than trying to graph the more difficult functions from scratch. So if you can figure out what the base function is, as you saw from our introduction board questions, our base functions are things like an absolute value function, a rational function, a cubic, a quadratic, a linear, or a radical function. Those are our main ones. If we can figure out what those are and we know those by heart, it's very easy to move them around. Okay, so for example, if I take a look at this function, y equals x minus 2 all cubed plus 1, my base function here would be y equals x cubed. And because this is one of our basic functions that we have, we should be able to graph this. So we know that when x is 0, y is 0, x is 1, y is 1, x is 2, y is 8, x is negative 1, y is negative 1, x is negative 2, y is negative 8. We can connect those together. Remember this curves. Oops. And arrows on our ends, or it needs to reach the edges of your grid. Okay. Then I need to decide based on my function I was actually given, what is happening? Okay. What transformations are happening? So if I take a look at this minus 2 inside the function, that's going to be right by 2. And the plus 1 at the end of the function means we are going to move up 1. Right. So again, I would choose to go point by point and move these things over. From the leftmost point, right 2, up 1, we're going to end up here. The next point, right 2, up 1, you'll have a point on your x-axis. Right 2, up 1, we go here. If you want to, you can start connecting these if you find it hard to visualize. Right 2, up 1, I can keep connecting. Right 2, up 1, this is going to end up slightly off of our grid. So this is our y equals x minus 2 cubed plus 1 graph. And my black one is the y equals x cubed. Okay. So we've been asked to state the x and y intercepts. So if I take a look at my blue graph here, my x-intercept is when x is 1. Okay. Or I can write it as a coordinate 1, 0. My y-intercept is y equals, looks like -7. Or I can write it as 0, -7. They won't always be perfect nice points, but just a reminder, your x-intercept is when y equals 0, and your y-intercept is when x equals 0. So you can do this algebraically as well. If I want to find the y-intercept, I can plug 0 in for the x in my equation. If I want to find the x-intercept, I can plug y is 0 into my equation and solve for x. Okay. We are being asked to state our domain and range. Remember, domain is what possible x values do we have. I could keep going left to right forever on this graph. So my domain is all real numbers. Your range is what possible y values are happening. And again, this thing has arrows on both ends. It's going to keep going up and down forever. So our range is all real numbers. Our last question is asking us if the point 5, 6 is on the graph of some y equals f of x. We don't know what function this is. Okay. What are the coordinates of its image point? Image point just means the point on the new transformed graph. So it wants to know, where did this move to? Okay. So we have to figure out what's going on here. So we see that, oh, my computer's thinking for a moment. We see that we have this new written way where we've got the +3 on the left side with the y. So I'm going to choose to rewrite this as f of x minus 1 minus 3, because I like to look at it that way instead. You do not have to do that. Okay. And we see that we've got a -1 inside the function with the x. This is going to be moving right 1. This means that our x values all have added 1 to them as we've moved to the right. Okay. The -3 at the end means we are going to move down 3. So what we are going to do is we're going to take a look at our original point, which was 5, 6, and we are going to say, well, where would this go? Okay. If my 5 moves to the right by 1, now it's going to be a 6. If my 6 moves down 3, now we're going to be at 3. The other way you might see this written is any point on our original f of x, xy, is going to map to moving to the right by 1, meaning our x would add 1, and moving down by 3, which would mean y would subtract 3. This is called mapping notation. So if a question asks you to explain the transformations in mapping notation, that's what it's talking about. Okay. You might see that in some of the questions in the textbook as you're trying some of the practice questions here. Okay, and that's it for 1.1.